I just want to start with a public service announcement. COVID is real and still around us. Please take necessary public safety precautions. I found myself having it, a day before I was supposed to travel. So it's been, at least I'm on the other side, but please be patient with me as I might cough and stuff. Yeah, let's stay safe. Thank you for accommodating me remotely and encouraging me to inviting me to give an inspirational overview on AMO systems to look for dark matter. It's not a talk I give usually. We always stick to our own research. And so it's been a fun exercise for me to kind of step back and zoom out. And this is definitely not a complete overview. In fact, I'd argue very incomplete overview, but hopefully inspirational one. And it's always awkward as a theorist, to be asked to talk about detector technology. So I'm kind of like finding my way to wiggle around experimental details. So thank you very much for coming over early in the morning to listen to me. So let me start with, of course, Zoom troubles. I'm going to stop sharing for 1 second and start sharing again because slides weren't moving. We have been using AMO systems to measure some of the smallest things we can. Using atoms, we can measure time to 10 to the minus 18 seconds, measure really weak magnetic fields, attotesla magnetic fields by watching some atoms slosh around in an optical trap. We can measure Yougto-Newton forces. We can use nanomechanical devices to measure zeptometer displacements or yoctogram masses. And so these are very small numbers, and as a theorist, you step back and you just go, oh yeah, spin one half, spin one half, spin one half, and harmonic oscillator, harmonic oscillator. And I do that because that's what my advisor taught me, that there are only two types of theorists. You're either a spin one half theorist or you're a harmonic oscillator theorist. And everybody can do this mental exercise, who they are. And it's not just because these are the two problems that we were taught early in physics and we really know how to solve them, well, to a great extent. They show up in a wide variety of situations. Spin one halves or spins in general, they capture transitions and coherences between energy states. Harmonic oscillators capture small changes around equilibrium, and these are situations that arise a lot in physics. So we also use these to measure really weak signals a lot. In fact, if you think about it, the energy difference between two energy levels that make up a spin one half system is very susceptible to weak external magnetic fields or variations of fundamental constants. And it is this susceptibility of the energy level to these things that lets us measure these weak changes in the local environment. And we use it all the time in magnetometers or NMR, MRI. Similarly, if you have a mass on spring system, a harmonic oscillator, classical or quantum, if it has a weak external force acting on it, it's gonna move, and you can monitor the position of your harmonic oscillator to get to know about weak forces that are acting on it. And this is the working principle behind AFMs or large-scale interferometers like LIGO. So despite a lot of these precision measurement techniques and being able to measure forces and fields and displacements to such small numbers, we still don't know what over 95% of our universe is made of, which is one of the reasons we're all here together. So we want to learn more about dark matter. And I want to talk about how a lot of this technology can be used to constrain properties of dark matter. So how do we know about dark matter, right? So the way we constrain our knowledge about our lack of knowledge about dark matter is to either look outside, do better and bigger astrophysical surveys. So whether it's the James Webb Telescope or LSST, we want to look outside and back into our cosmological history and be able to know more about dark matter or dark energy. And the second way is to, look inside, do direct detection experiment, try to measure the very weak interactions between dark matter and normal matter. And it is in this category that pretty much most of the small scale experiments looking for dark matter come in. And I'm sure you've heard a lot of talks about the uncertainty in dark matter. We know very little. There's about 90 orders of uncertainty in the composition of dark matter. And that leads to the fact that you need different types of detector depending on what dark matter is. So in Earth-shaped volume, there is estimated to be about 100 grams of dark matter, which according to this cartoon and your calculations, a little bit of Googling, is about 1 squirrel mass. And that's the problem with detection of dark matter, because if all this mass is concentrated in like a squirrel size object, then you can measure it using gravitational interactions alone, using your weighing machine. But what are the chances that squirrel-shaped rock of dark matter is on top of your weighing machine? You're looking at a very rare event, right? Instead, if this mass is distributed in this very fine ultralight dark matter particles that are much, much lighter than the neutrino, then you have a persistent signal. That thing, that dark matter signal, is always there, but you're not going to be able to use your weighing machine to measure it. So we have to look for non-gravitational interactions. And so depending on the mass and other things, one has to design very different types of experiments. So for astro candidates, you pretty much look outside. One can use recoil detectors to constrain object-like or particle-like dark matter. And for wave-like dark matter, it's typically resonant amplifiers because it's a narrowband signal. Of course, we don't know the frequency of that signal. So if there is a new particle with mass less than 1 eV, just given the local dark matter density, it must be bosonic. And this signal is the signal, because of this type of dark matter, would be wave-like. We wouldn't know the frequency because we don't know the mass of this new particle. And it is locally coherent for 1 million oscillations. So there's a narrowband signal, some cosine omega t, that is always there in your lab. You just don't know the omega. And that's the kind of signal that I'll be focusing on completely, the ultralight dark matter regime. Is there a quick question, or am I just hearing it? Okay. So I personally, I'm relatively new to the field, just 3-4 years old, maybe even less. And I've found that it is very helpful, and I'd like all the students in the audience, I'll encourage them to think about it that way, that before you go thinking about dark photons, which is if this new particle is a spin 1 particle, that's what people call it. try and think about normal photons. You know, if you were blind and I told you that there is this magical particle called a photon, and there's a lot of it and it's everywhere, how would you convince yourself that there is this particle called a photon? Right? Now, and there'll be lots of them. Right? So if you will have to sit down and design an experiment. And I said there are two ways to convince yourself that there is this thing called a photon. One is a direct detection experiment. So anything where a photon acts as a real, photon as a real particle, something measurable. So think of photoelectric effect, for example, right? So you have a real measurable signal, and the signal is only there because there is this particle called a photon. So that's a classic example of a direct detection experiment. Or one can think of Coulomb's law, right? That is where photons as virtual particles mediate forces. So one can think about like the fact that you have Coulomb's law, this attraction between two opposite charges, is proof that there is such a thing called a photon. Okay. And there is a clear analogy between these things and dark photons, or actually in general, all kinds of ultralight dark matter experiments. So a haloscope experiment is a classic direct detection experiment. And the EP violation bounds are an indirect detection experiment. So all kinds of these fifth forces bounds would be where this new particle, this ultralight dark matter particle, is mediating forces. And I found to kind of like going with this analogy really helps me drill down on various things. And another thing I have found very useful is to remember that if there is a signal that's always there, then you have to think very carefully about a differential measurement scheme. What I mean is, if suppose I'm getting bigger and smaller because of interaction with dark matter, and my ruler is also getting bigger and smaller because of interaction with dark matter, then how do you know that you got bigger or smaller because of interaction with dark matter? One has to think very carefully about what your ruler is made of, right? So you need a ruler that does not interact with dark matter, or you need a ruler at least that interacts differently with dark matter than you. And there's a nice analogy with the ether experiment of 1887, Michelson-Morley, where the idea was that we're all swimming in this ether, and Earth's dragging it, and so you should see the speed of light being different this way versus this way. So it's a nice differential measurement that can be used to constrain properties of the ether. And so I worked with Mariana, and there's a nice review that everybody in this community helped write about a variety of small scale quantum experiments, actually some classical ones as well, used to constrain ultralight scalar and vector dark matter. And I was gonna give a bit of an overview of all that. And then I realized how much time I have, and that there are many other people giving talks about all of these subjects, and how I'm just not an expert at many of these things. So I've decided to, stick to the overview theme, talk about one of these things where I have made some contributions, and then, talk about some general ideas. So I already shared with you my personal philosophy and intuition into ultralight dark matter detection, my philosophy and insight. I will be talking to you now about some mechanical dark matter detectors, and I'll end with an overview of quantum optics techniques to look for dark matter. By mechanical systems, I mean simply mass on spring, like literally mass on spring like systems. So these could be pendular mirrors as used in LIGO, or a couple of atoms sloshing around in an optical trap, or often suspended mirrors or membranes. And these kind of floppy mass on spring like systems have very good force sensitivities or acceleration sensitivities or strain sensitivities. And our work was on using them to constrain scalar and vector ultralight dark matter. So how do we use a mechanical system to look for dark matter? Well, remember mass on spring, and it goes haywire when the spring resonance frequency is the same as the periodic external force drive. So that's the same idea. You can use a mechanical system as a resonant amplifier for a continuous signal, or you can use it as a single phonon detector, or you can use it as a weak recoil detector, or you can put it in your gravitational wave detector and try to constrain astro candidates. So to start with, I just want to say mechanical systems have already constrained all these types of dark matter. LIGO LIGO black hole merger statistics were used to try to constrain primordial black holes as dark matter candidates, and these statistics were challenged as well. So it's an interesting area of research people are looking into. Levitated nanospheres or microspheres have been used to constrain object-like and particle-like dark matter in David Moore's group. There's a bunch of interesting papers. And mechanically constraining wave-like dark matter has primarily been cavity-based searches, and I see there have been some talks on that already. And I'm sorry, I'm missing all of them. So my talk will be all about resonant amplification of a continuous signal. And this is not just my work. There have been a bunch of proposals and some new results in the area. I will only be talking about 2 of these, but we learned a lot from all those who came before us. If you have scalar dark matter, then it can modulate fundamental constants, and changes in the mass of the electron or alpha will make every atom go big or small. If you have a ruler made up of atoms, then that ruler or any macroscopic body, me and my ruler, are getting bigger and smaller. And this effect is further amplified on an acoustic resonance of the ruler. And the differential part is that hopefully me and my ruler would have different acoustic resonance frequencies. So that's how you look for this length change effect. And there've been a bunch of new constraints that have come up to constrain the mass of the electron. I want you guys to focus on this little sliver called Auriga. And when I started in the field, I used to call them scooping plots, because every new experiment comes along and there's like a little scoop, and then somebody else has this little scoop. And in a sea of scooping plots, you sometimes see these spikes. So Auriga is this nice spike that is very narrow band. So it only looks for a very narrow range in dark matter masses, but it digs really deep. So you can have access to very weak couplings between normal matter and dark matter. And this is the advantage of this resonant enhancement in this mass on spring-like systems. Auriga is a 1-ton resonant mass gravitational wave detector, data from which was used to constrain isotropic strain due to scalar dark matter around its resonance frequencies. So our work was about using systems that were much smaller, few centimeter scale thing of superfluid helium to quartz bulk acoustic wave resonators, sapphire pillars and stuff, and looking at their acoustic modes and how we can constrain mass of the coupling to mass of the electron or alpha using small scale millimeter or so mechanical systems. And somebody, the group of John Davis actually was inspired to build a system to do this. So we have Helios, the superfluid helium-based ultralight dark matter optomechanical sensor, because you need to have like a nice acronym thing for your experiment. And the cool thing about making a mass on spring with superfluid helium is that by changing pressure of your container, you can change the acoustic modes. You change the speed of sound, which changes the acoustic modes of superfluid helium without sacrificing your Q factor. So you can change it by many hertz by just sweeping the pressure. And that allows you to do a scanning search. So not just a tiny sliver, but a few tiny slivers, similar to the cavity haloscope experiments, where you can really do a nice sweep in your parameter space. So we're working with his group to build, to basically set new constraints. Another example is vector dark matter that couples to different, so for example, a baryon or baryon minus lepton number. This kind of thing would give you a differential acceleration signal. This is also another example of like, if every mass is accelerating, how do you know you're accelerating in a dark matter field? If you have a material dependent acceleration, then you connect to materials that have different composition, and then you would have a differential acceleration, and that can be measured. And this effect is further amplified on an acoustic resonance. So that's the general idea behind vector dark matter detection. And we looked at a silicon nitride membrane coupled to a beryllium mirror and looked at its thermal noise and how we can resolve the thermal noise over the imprecision and back action noise. I'll talk briefly about it later, around the one of the resonances of your membrane. And nothing is a single mode harmonic oscillator. So you can look at higher order modes or have membranes of different sizes and be able to constrain coupling to B minus L or baryon number. And this is a project being pursued in Dalziel Wilson's group at the University of Arizona. And more generally, there's a bunch of ideas in using mechanical systems to constrain ultralight or not so ultralight dark matter, and that are discussed very nicely in this review that I'd like to point you to. I think my slides will be up at some point later. So, and as you have probably been hearing about, there's a bunch of beautiful experiments and new data coming along in constraining all types of scalar and vector ultralight dark matter. And I wish I was at the conference to hear more about all of these results. As a general rule of thumb, every time you see spikes in this Scoopy plot, you know that there's these resonances involved. And yeah, okay, so that brings me to the third and part of my talk, which is another overview, a little bit about quantum optics for dark matter detection. And I should say I'm a quantum optics girl. So I've been missing my A's and A daggers, and these were, it was a lot of fun to think about it and prepare these slides. So going back to the dark photons and how I asked, if you were blind, how would you know they're photons? And I said that this is a similar analogy you use to look for ultralight dark matter. I kind of swept like a very, very important thing under the rug, which is that this signal is much, much weaker than its bright photon counterpart. So you're trying to measure a very, very weak signal. But that's where new physics is, right? Like today's signal is tomorrow's noise floor. So one has to kind of dig through to look for a new signal. If you look at Michelson-Morley's experiment and then LIGO, LIGO's first gravitational wave signal, there is 129 years between them. And a lot of it has to do with how much the y-axis changed. 10 to the minus 21 is a very small fractional length change. Our galaxy is 10 to the 21 meters long. So you're trying to measure a length change of 1 meter over the size of our galaxy. And when people are trying to do precision measurement like this, sometimes quantum mechanics stands in the way. So imagine you were trying to measure position and you do it with some uncertainty, delta x, probably small. If you do that, you're going to have some delta p. You're going to give a recoil kick to whatever it is you were measuring the position of, let's say a harmonic oscillator, right? So you gave a momentum kick. The problem happens that at a later time, x at a later time is dependent on p at 0, right? So whatever your x is going to be at time t, it's going to be impacted by that recoil kick that happened a while back. And if you keep monitoring x, this error is going to keep building up. This is the position measurement back action, and these back action effects are built up by repeated measurements. So if you're continuously monitoring, you end up building up the error in your X measurement. And that's a bit of a problem. And this was a problem that was recognized in, I believe, in the seminal paper in 1980 by Carl Caves, in an abstract that is every theorist's, dream to write. It wrote it with some great conviction that, the quantum noise in the quantum radiation pressure fluctuations disturb the position measurement. And he did that definitively and detailed back action noise, and in the subsequent years, ways to get around this back action noise. So the idea is simple. If you're trying to use light to measure position, you don't shine a lot of light, you have imprecision noise. You don't know the position at all. You shine too much light, and now you have back action noise. You have imparted too many momentum kicks. And sitting at that sweet spot where in your light power, that's your standard quantum limit. And it's standard barely, and I'll talk about that. It's quantum just because light is, discrete. That's it. So it's not like that quantum. So there are many ways to go around the standard quantum limit, because this was another thing that my advisor taught me, that there are no problems in quantum optics, only features. So standard quantum limit is not a limit. You can, and Carl, I believe in 82, had a paper about it. You can just inject squeeze vacuum. If you, to go below the standard quantum limit, and this has already been implemented in a dark matter search, and I talked to you all about X and error in X at a later time because you were trying to measure X. Instead of measuring X, which is A plus A dagger and doesn't commute with your Hamiltonian, you can just measure N, A dagger A, that commutes with your harmonic oscillator Hamiltonian. And then you won't have this back action problem because there'll be no momentum kick. And so that kind of idea has also been implemented very recently. And the fun part is that there's a lot more ideas about how to get around these quantum noises, because as I said, it's no limit. Including, for example, more broadband way of doing this using back action noise cancellation, which is a quantum version of Bose noise canceling headphones that you would see. And here you couple it to another harmonic oscillator, but with a negative mass. This is where a little bit of the A and M of the AMO, there's like atomic systems coupling that you can use. But there are ways to do this. And this is an active area of research, starting from 2010-ish or before, all the way to last week. There's a bunch of ways to avoid this type of quantum noise. So I would say there are exciting times ahead in using quantum optics techniques, not just back action noise cancellation, but the feedback control and others to mitigate quantum noise and get around the standard quantum limit. And so with this, I would say that, yeah, these are my thoughts on the topic. So we went over an overview of ultralight dark matter detection. So think about yourself as swimming in a sea of photons, but being blind to them, and thinking of ways to convince yourself that there is this sea of photons that you're blind to. And then we talked a little bit about mechanical dark matter detection, which is mass on spring, and you can set tight bounds on normal matter, dark matter interaction because of resonant amplification. So when the external drive force, which is periodic for narrowband dark matter signal, is at the resonance frequency of your oscillator, you can set very strong bounds on dark matter around those masses. And finally, I talked a little bit about using quantum optics techniques to mitigate the measurement noise, and how this subject is in its infancy. And there's a lot of techniques that were used for gravitational wave detection that were thought of and then used for gravitational wave detection that can also be implemented for dark matter detection. You know, I'm a theorist, but I am aware that at a kilohertz, to set new bounds on mass of the electron coupling, for example, you need to measure strains less than 10 to the minus 20, which is hard. And to set bounds on B minus L coupled vector dark matter, for example, at around a kilohertz, you will have to be able to measure accelerations less than 10 to the minus 11 meter per second square. And these are heroic experiments, and these are going to be hard to do. But you could ask me, and there's all types of people here, what if dark matter is not ultralight? You know, maybe you have your own favorite candidate of dark matter and you're convinced all of dark matter is that dark matter, right? And I would say, you know, if I'm feeling particularly snappy, I might just say, really? How do you know dark matter is not ultralight? There's only one way to know. You have to look. But it's a little bit more, you know, I keep showing this figure from Michelson Morley's 1887 paper, and the dashed line is the theory of what they should have seen. And the straight, like little jaggedy line is the solid line, is the data. And, you know, the data convincingly did not match the theory. They did not see the signal that they were looking for. And it's only because they did not see that signal that we have a better understanding of the nature of light. And I firmly believe that whether, you know, where you see dark matter signal, whether you see dark matter signal, these things like are not, well, they are relevant But what is important is that we have to look everywhere to be able to constrain the available parameter space. So if we want to understand the composition and properties of dark matter, we have to kind of look everywhere. And, and in some places you won't find it, but you will still learn something about the nature of dark matter. So with these thoughts, I'd like to, stop talking. And these are my students who have been doing all the hard work that I talked about. I've been working very closely with a colleague from Haverford, Daniel Grin, who has been telling me about cosmology and teaching me a lot of things, and work closely with two experimental groups, Dalziel Wilson and John Davis. And I'm happy to take your questions. Thank you very much.